let's go ahead and include all the features for our data set. Let's use all 4 features to predict gas consumption. Now, our model, if I go back here, let's sketch out our model. So we're saying that the predictive gas consumption is equal to an intercept term times a coefficient for all our variables. So these are a coefficient associated with all our variables. And one way to view what these coefficients represent is these coefficients represent how much of a change, if you change one of these variables, how will it affect the predictive value? In other words, if our median income increases, how will that affect, how will that translate to a change in gas consumption? If we change the amount of miles of paved highway, how does that change the predictive value for gas consumption? Because there's a linear relationship between the predictive value and our features. So given this definition of beta, or one interpretation of these beta coefficients, then we can use this to derive, to analyze, do some after-the-fact analysis, after we train our data, of which features were most important, which features really, which features are most important. In other words, if you do a change of one feature, which one will have the most dramatic change in the gas consumption. Now, at the moment, what are some concerns if we just inspect the beta coefficients after the fact? Are there any concerns? Is it fair to compare across all our features, beta 1 and beta 2? In other words, is it fair to compare the beta 2, the value for beta 2 compared to beta 1? Is that a fair comparison? Let's think about that. Well, it's not going to be a fair comparison at the moment because we understand these features vary with different scales. Paved miles, it's going to exist in a different scale than the fraction of the population or the median income, things like that. All these features have their own scales that vary widely. Looking at these beta coefficients, it's not going to be a fair comparison. But we can go ahead and do something to our data set such that any resulting beta coefficients we can easily compare across all the fields, easily compare across all the features. So what should we do with our data set such that any derived beta coefficients we get from our model we can better analyze? What should we do? Well, as I mentioned before, the problem here is scale. These features exist in different scales. So what if we rescaled our data? What if we rescaled the data such that all the features exist in the same scale? So one way to accomplish that we've seen so far is our standard scaler. So let's go ahead and scale our data such that the features have the same scale, train a linear regressor, inspect the beta coefficients, and then we have a fair base of comparison for our 4 features. So let's go ahead and do that and derive some insights. So now you'll see one of the nice things about the linear regression model. I can write out this model. I can write out the functional form of this model. It's a lot easier to understand. It's not a black box. I can easily inspect. I can see how it works. Oh, there's a linear relationship between the features and the value I'm trying to predict. It's governed, the strength of that relationship is governed by the beta coefficients. I can do some after-the-fact analysis to see which feature was most important. So even though it's a simple model, I can learn more about what's going on with my process with this simple model. We'll see that with other simpler models. More complicated models, a little harder to derive insight. We'll try our best. But now we see one of the important things about using simple models. I know some people tend to put down simple models, oh, linear regression, but why not? Let's try it out. It's a very simple model, easy to train. We can derive some insight before we go on to more complicated models. Another reason why simple models are important is because they serve as good benchmarks. Hopefully when we use a more complicated model, we'll do a better job than the simple linear regression model. Sometimes it does a slightly better job and we have to ask ourselves, well, was it really worth it? Maybe we sacrifice a lot of insight or a lot of intuition we can get from our model if we use a more complicated one, and maybe it's not worth it given the small boost in performance that might happen. Anyways, I'll stop with that digression. Let's go ahead and back the notebook and let's do some scikit-learn. Alright, so I have my linear model, and of course I'm going to use pipelines. Okay, so I'm going to create my scalar. Let me just import my scalar. Scikit-learn pre-processing to the pre-processing module. Import standard scalar. And let's see. Okay, let's construct my pipeline. First step is my scalar, so I'm going to just call that scalar. Remember, these names of these steps are arbitrary, but it's nice to give them something meaningful. And my regressor, I'll just write it all out. Regressor. Another nice thing about pipelines is that I can easily swap out this model with another model. Just switch that part out from my workflow. And that's why some of the names here, I like to just use more generic names. It's a regressor, not any type of regressor, but it's just a regressor. So I can go ahead and use a different regressor if I wanted to. I could go ahead and use a different scalar if I wanted to. That's why I like to keep these names as general as possible, but telling you what it's doing there, what that step does. Okay, so that's my pipeline, and there's a lot of parentheses to keep track of, but I think I have it all set. Let's go ahead and fit. Okay, let's fit. Let's put gas, and what was let's see, let me just look at my data set so I can do this properly. So gas, this is my data set there. So I'm trying to predict this last variable. So let me create x and y here. So x is going to be, let's see, x, give me tax, give me income, give me highway, give me drivers. Okay. Let's see. There you go. So I dropped that. I could have just dropped a column, but wrote them all out there. And then y is going to be prices. No, I believe it's just gas. Okay. Let's just do this shape here. Okay. That seems to work. Okay. Error message there. Let's see what the mistake. Too many values to unpack. Okay, must have messed up in my parentheses here. There you go, I missed a parenthesis right there. Okay, fit my pipeline. Now let's go ahead and inspect the coefficients. Now this might be a problem initially because we're using pipelines. We're using pipelines, and now I want to retrieve some attribute for a step in the pipeline. So this is good practice with pipelines, understanding how you can go ahead and pull out units after you've trained them. So with the pipeline, there is a named stepped attribute. So if I run that, that's a dictionary with the name of the step that I gave it with the estimator that belongs to that step. So I said regressor. So I'm going to say LR, linear regression. So there you go. So now LR is the name for this object that was trained. So that's how I can pull out that step. And the reason I want to do this is because I can look at the coefficients. There you go. So there are my coefficients. So with these coefficients, let's inspect which one has the largest magnitude. And if we go back here, so this one here has the largest magnitude, and that represent drivers. And the next largest one was income, and the lowest one was highway. So this says that of all our four features, the one that was most important was the percentage of drivers, which makes sense because remember that initial data exploration, we looked at that visualization, we changed, we're plotting what we're trying to predict with respect to all those 4 variables. And we said to ourselves, you know what, it looks like this percentage of drivers probably has the greatest impact. And sure enough, when we look at the analysis, that one has the largest coefficient magnitude-wise. Largest coefficient magnitude-wise, after we scaled it. Remember, we scaled it so they're all being compared against the same scale. This one has the most influence to the predictive y value, the value we're trying to predict. And the second largest, sort of a bit of a tie, not a bit of a tie, but the next two that are rather close to each other are the tax and the income. And we saw that with the visualization, there was some trend, right? But we also noticed it was a negative correlation. So in other words, we increased the tax percentage, the gas consumption decreased. So we saw that relationship. And sure enough, the coefficient is negative. So it's got a negative correlation. Remember, when we're comparing these magnitudes, we want to compare magnitudes, absolute value. And the one that had the least influence to the predictive value is the miles of paved highway, which we looked at and we understood, we saw that. I said, you know what, this variable is probably not going to help us out too much. And we clearly see this played out when we look at the coefficients. In fact, we can go just actually generate percentages if we want. It'd be a little fancy that way. So we can do something like LR coef. Just dump this to a variable called coef. We can do coef divided by NP abs of coef, and there's sum. Let's see. Yeah. Do NP. You can just do NP absolute value. So this is just generating them in terms of a fraction. That makes it easier to compare. Yeah. So it's another basis of comparison, looking at the fractions. Okay, so that matched up with the model telling us, matched up with the initial intuition that we gained, the initial analysis that we did for our model, for the problem we are working on.